Hello, everyone. Welcome to MACSMIN 2025. And now Professor Xiaocheng Shang from University of Birmingham will talk about stochastic Norton dynamics. Over to you, Xiaocheng, please.
All right, and thank you very much for the introduction, but also for the invitation as well. It's a great pleasure to be here, and apologize that I have missed the first 2.5 because I was at another conference somewhere else on this beautiful campus, which I had agreed to participate first. But it's a great pleasure to be here, and I also apologize for changing the title. Today I'm going to talk about the stochastic Norton dynamics. Which I will try to convince you it's an alternative approach for the computation of transport coefficients, and particularly in the context of the so-called distributed particle dynamics. I will try to explain everything on the title here. And also feel free to stop me if you have any questions. Yeah, very briefly.
Leave full screen. Leave full screen so and it'll picture.
Okay.
And then try changing slides.
Escape usually.
Yes.
Okay.
Great.
Thank you. Okay. Let me first very briefly to mention what's this transport coefficients, and the transport coefficients. The transport coefficients typically measure how rapidly a perturbed system returns to equilibrium. And for example, we have like mobility, diffusion coefficient, and shear viscosity. And there are various ways to estimate the transport coefficients. And for example, one of the most famous one is the Green-Kubo formulas here, and which is typically an integral of autocorrelation function, like this one here. Like this one, as the one here, which is, so when the autocorrelation function is a velocity autocorrelation function, as we can see from here, so we can use the integral of this autocorrelation function to estimate the diffusion coefficient. And when it's the stress autocorrelation function, we can use the integral to estimate the shear viscosity, as we can see on the right here as well. But there are also some well-known issues with this famous approach. And for example, when we do this integration, it's unclear where we cut this off when we do to determine the range of this integration, because it's well known we have some long-time behavior for this kind of autocorrelation functions. But also because this is the equilibrium approach, the signal-to-noise ratio is particularly unfavorable, which means that we have to typically run the simulation for a very long time, and often we have to run many independent runs to try to reduce the variance. And therefore, people also use another famous approach, which is non-equilibrium molecular dynamics, which is particularly invented to try to improve the signal-to-noise ratio, as I just mentioned. However, although this signal-to-noise ratio have been improved in this non-equilibrium molecular dynamics approach, it still suffers from, for example, large statistical errors, which means, again, we have to run very long trajectories to have a good estimation of this transport coefficient. And the way this NEMD approach works is that we add an additional force, which is non-gradient, and try to generate some additional responses like what I'm seeing here in blue. And then in the linear regime, we can use this famous linear response theory to estimate the transport coefficient. So this is a typical way to use the non-equilibrium molecular dynamics to estimate the transport coefficients. But today, I'm going to talk about something very different, which is actually the opposite. Because as I mentioned in the NEMD, we fix the force we add is fixed. We actually fix the forcing and then measure how strong the flux generated by this additional forcing. But for the Norton dynamics, it actually works completely the opposite. For the Norton dynamics, we actually fix the value of the flux and then measure how much forcing we needed to induce that flux. It was actually first invented by Evans and Morris in the 1980s. It was only recently extended to stochastic setting, specifically in the Langevin dynamics by the group of Gabriel Stutz in Paris. And we also recently had a paper where we further generate this idea to in distributed particle dynamics, which I will also explain in a moment. And this was very recently published in the Journal of Computational Physics this year. And also let me give you a brief overview of this distributed particle dynamics. It's actually, it's actually like it works at the mesoscale because I just learned the Unilever is in the first floor of this building, and they also do lots of DPD simulations, particularly on surfactants. And actually the mesoscale, the DPD, covers a wide range of time and length scale. As you can see, it's one of the mesoscale modelings. And I'm particularly interested in this method because it's also particle-based, like the famous Langevin dynamics. So it's between molecular dynamics, but also continuum mechanics. It actually covers a wide range of time and length scales and has loads of applications. And also particularly DPD is a coarse graining technique. So when we talk about one DPD particle, it actually represents a number of smaller particles, as we can see from this picture here. And also typically we will use a soft and short range of potential, but sometimes we can also use, for example, Leonard-Jones potential as well, which is actually the choice in the Norton dynamics paper. As I mentioned, the DPD has a large number of applications, as you can see from this nice picture borrowed from this paper here, and particularly like a polymer DNA, colloids, phase separation. It covers a wide range of applications, and particularly you can find a very nice movie about these red blood cells, where this microfluidic device, like those right here, they can actually pick out these green tumor cells from the red blood cells simulations. It's a massive simulations. So it's very important if we can, develop some nice and numerical algorithm to speed up the simulations while maintaining good control over transport coefficients, for example. So this is a very quick overview of the distributed particle dynamics. And now let's look at the formulations. So for the DPD, it's actually, you can view it as a combination of this Hamiltonian dynamics for this part, but also it has a thermostat where this gamma, the term with the gamma is a damping term, but also we have a noise term at the end here. And the gamma here is a friction coefficient, and the sigma is the strength of the noise. So W here is a white noise. It's a Wiener process here. And the nice property of the DPD that all the forces here are pairwise and act along of the line of centers. So therefore, both linear and angular momentum are conserved. And as I mentioned, although in the traditional setting, people typically use a soft and short range of potential, but something like a shift Leonard-Jones can also be used, which is a choice in this paper. But the results are very similar if we use a standard soft potential in this particular paper here. And RC here is a cutoff radius because we only consider the interactions within a range of like RC just to reduce the computational cost. So this is DPD, and we also have this fluctuation dissipation relationship between the two matrices appearing in the equation of motions, and also between the sigma and the gamma here. And then if we have this fluctuation dissipation relations, the DPD system preserve a canonical ensemble invariant measure like this one here, where the H is the Hamiltonian of the system and the beta is the inverse temperature. And this is just to mention that it has momentum conservations in each directions. So this is very nice, which means that it's a constant temperature techniques like thermostats. And now let's look at what happens when we apply the non-equilibrium molecular dynamics in DPD. And particularly, as I mentioned, in the NEMD approach, we add an additional force here, which is the red term here. So F here is the additional force, which has a unit magnitude. And the eta is the strength of this force here. And the FQ here is typically non-gradient. And then we can use the linear response theorem to estimate the transport coefficient alpha by using this formula here. So as you can see, here we fix this eta, which is the strength of the force, but measure this response R here. So R here is the response observable. And in this particular paper, for simplicity, we choose this particular form of this response observable, but it can be extended to some other form as well. So the choice here just for simplicity here. So it's just like a function of Q times momenta here. And then for the Norton approach, as I mentioned, in the Norton, we don't fix the flux, we don't fix the force, but instead of fix the flux, which is R here. So in the NEMD, we measure the R here, but here we fix the R all the times, but just try to measure how much forcing we need to induce this flux here. And I'm not going to talk about the technical details here, but just to mention, for this particular choice of the observable, response observable here, we can actually write down the forcing observable lambda here as follows. And then we can estimate the transport coefficients using this formula here. As you can see, in this case, we fix the flux. We fix the flux, but measure how much force we need to induce the flux. So it's like it works completely the opposite. So you might be wondering why do we do this? Then I'll show you why the advantage of the Norton approach here. Let me show you some results when we try to measure the mobility, which is proportional to the diffusion coefficient. And we tried two cases. The first is when we apply two drifts, where we only apply this additional force on two particles. They have the force have the same magnitude, with completely different directions here. As you can see, we only apply the additional force on the first particle and the second particle here. But for the color drifts, we apply the additional force on all the particles. If we assume the number of particles is an even number, then half of the particle will have the force in that direction, but another half will have the force in that directions. And again, the magnitude of the force are the same, but just different directions. So now let's see how it works. So here we look at the response profile, which, as I mentioned, is in this particular form. And actually, for the computation of the mobility, it looks like this one here. And the F is the additional force, and the M is like a mass matrix. Typically, it's diagonal. And what we are seeing here is on the top row, that's the results when we apply the two drifts. In the two drift case, we have the black line is a reference response profile, and the blue one is results from the non-equilibrium molecular dynamics, and the red one is the Norton results. And in the two drifts case, we can see the Norton is slightly closer to the reference on the top left plot here. But if we have a much wider range of the forcing, as we can see on the top right plot, we can see both NEMD and Norton are pretty much similar to each other. When it's in linear regime, they are very much close to the reference value. When it's in the nonlinear regime, they also stay very close to each other. So this is like an indication that we can indeed use this Norton as an alternative approach for the computation of transport coefficients. And in the bottom row, that's the results when we apply this color drift, where we have all the particles will have some additional forces here. And again, the results are very much similar as in the two drifts case. Particularly both NEMD and Norton are, very much, the results are very much similar between Norton and NEMD, even in the nonlinear regime, which is again a demonstration that we can use the Norton to estimate the transport coefficients in DBD here. And we also tested how this mobility estimation will change when we change the value of the friction coefficient, because the friction coefficient is typically, determining the dynamical property of the system. And we can see again, both NEMD and Norton are stay very close to each other when we change the value of the friction coefficient. And also on the right, we can see when the friction coefficient is large enough, it recovers the expected slope of -1, which is between the mobility and the gamma over there. So this is really nice. And you may ask, why actually do we want to use Norton over the traditional NEMD? And so here is the part of the reason, because if we use the Norton dynamics, because you may remember, as I mentioned, the issue with the NEMD approach is it has large statistical errors. But if you use Norton dynamics, it will be able to reduce that. And if we look at this asymptotic variance, which is what we are trying to plot here, we can see that on the left, when we have relatively small friction coefficients, the Norton is slightly better than the NEMD approach. But when the friction coefficient is larger, we can see the Norton clearly outperform the NEMD, particularly when the force is relatively large here. And also, very nicely, both the plots here recover the expected slope of -2 here, because that's what you would expect from these two formulas here. And this asymptotic variance should have like scales eta to the power -2 here, and also to the r over the -2 here, and for the Norton dynamics. So this is the results for the mobility, but we also tested the results for the shear viscosity, which is a little bit more difficult to measure. And in the shear viscosity case, we also apply an external force, but then the additional force will look like this. So additional force will be on the x component, but that will be depending on the coordinates in y here. And we tested 3 different choices of the external forces for the computation of shear viscosity. The first one is a sinusoidal force, and the second one is piecewise linear force. But then the last one is a piecewise constant force. So 3 different forces here. And then we again look at the response profile for the 3 different forces here: sinusoidal, piecewise linear, and the piecewise constant here. But in each of the cases, as you can see, it behaves very much similar to the mobility case, where in both the linear, but also the nonlinear regime, both NEMD and Norton are very much close to each other. So again, it's a strong indication that we can use the Norton to as like alternative approach for the computation of transport coefficients. And here it's just like in the shear viscosity case, the response observable looks like this one here. And in the shear viscosity estimation, particularly in DPD, we have to derive a closed form expression for the shear viscosity nu here, which is different from the formula as in Langevin dynamics. So this is another major contribution of this paper. So what we are seeing here is with a plot of the F1 over U1, which is this term here, against the number of particles. Here we're just testing how this like F1 over U1 behaves as we change the number of particles here. But again, as we can see, both NEMD and Norton are, matches very well when we change the number of particles here. But also, if we look at the log-log plot, it actually covers the expected slope of -2/3 for both NEMD and Norton. And also just to mention, so because the reason why we measure this F1 over U1 is because rho is the particle density, which is constant. Ly is the length of the box in the y direction, so again, it's a constant. Only the F1 and the U1 are like variables here. We need to, and that's why we plot F1 over U1 here. But also we also plot this U1 over the friction coefficient to see how it behaves. And the reason where we only plot the U1 is because in this formula, with the three different choices of the external force, the F1 is actually analytically known. So we don't need to estimate. We know the exact solution, exact formula. So in this formula of the shear viscosity in dPt, we only need to estimate the U1 here. So that's why we only include the U1 in this plot. So here we look at how this U1 behaves as we change the friction coefficient. And also finally for this part, we can look at the key measures, which is the asymptotic variance, which is appropriate to mention that a lower asymptotic variance will mean that it will have like lower computational cost. So that what we are really trying to achieve is that by using the Norton approach, we will have a smaller asymptotic variance, which means that we will have like a smaller smaller computational costs. And again, the result is similar as in the mobility. When the gamma is relatively small, the Norton is slightly better than the NEMD. But if you look at the right-hand side, when the gamma is relatively large, the Norton actually clearly outperforms the NEMD approach, which means that we don't have to run as a very long trajectory as in the NEMD approach, which will save you a lot of computational times here. So this is the first part of the talk. I'm happy to take questions if you have any for this part.
So could you state maybe in non-technical terms what is the large problem in your area that you try to solve?
Yeah, for the computations of transport coefficients, the major problem is large statistical errors, which means you typically have to run very long trajectory and many independent runs.
Okay.
So if you can come up with some techniques where you have smaller statistical errors, which means that you don't have to run that long trajectory, you don't have to run that many independent runs. So it will save you a lot of time.
And if this aim is achieved, then how would it open? What would be the next higher level problem? If
in applications,
yes.
We are not actually thinking about application at this stage, but this is more like numerical techniques. But I think it's quite general. You can use it to whenever you want to calculate the transport coefficients in DBD, you can use this.
I think I will give example in my talk.
Thank you so much.
Your talk will be related.
Because we try to estimate the mobility of ions.
Okay.
And we use classical molecular dynamics methods. So maybe one of these approaches can be helpful.
Yeah. So the paper I mentioned by Gabriel Stills and his students, and they had this results in non-German dynamics, which is people often use non-German dynamics for molecular dynamics simulation. But my talk is mostly focused on distributed particle dynamics.
Okay.
Any other questions?
But what is this speed up that you can
You mean the
achieve?
actual speed up?
Yeah, compared.
Well, we don't have a number at the moment, but you can see particularly in here, the asymptotic variance is clearly much better than the NEMD approach, but we don't have an exact number at this moment. But
And dodging variance tells us about accuracy.
yeah, it's basically this tells you if you, for example, if you run the same length of the trajectory, same number of independent runs, then this will tell you the difference in terms of variance. But then on the other hand, if you want to achieve certain level of confidence or variations, then if the method with a lower asymptotic variance you just need to, you can run with much less time to achieve the same level of like variations or accuracies. If the method with a large asymptotic variance, then you have to run it much longer.
But because this DPD uses coarse graining,
Yeah.
so it's going to be like way cheaper. But the question is,
Yeah. It will be
order of
cheaper.
magnitude, or it's like factor of 2.
I don't have a number, I'm afraid. But as you're right, the DPD is like coarse graining. It will be much faster than atomistic simulations. But we are comparing like simulations in DPD. Like for example, we all use DPD, and maybe some people use NEMD to estimate the transport coefficients. It takes that much time to have certain accuracies, or we can use much less time to achieve similar accuracies, for example.
Okay.
Yeah,
Thank you.
let's move on. And then the second part of the talk will be focused on a particular issue in the DPD, which is the Schumpeter number issue. And in this part, I will focus on the standard soft and pairwise potential people typically use in the standard formulation of DPD, where we also have a cutoff radius RC here. It's a very soft potential, and that's why even like with this kind of soft potential, even the DPD particles can penetrate with each other, so that you can use much larger step size as would be possible in, for example, in a hard potential in molecular dynamics. And for the Schumpeter number, it's actually quite important quantity that characterize the dynamical behavior of fluids. It's actually a ratio of this kinematical viscosity nu over the diffusion coefficient D here. And the kinematical viscosity is basically the momentum and diffusivity. The diffusion is actually the mass diffusivity. And in a typical fluids, you would probably expect the momentum will diffuse much faster than the mass. And then we would expect the Schumpeter number to be in the order of 1000. But for a gas, you would expect the momentum will diffuse as fast as the mass. So therefore, you would expect Schumpeter number in the order of 1. And then we looked at this very popular parameter set people typically use in DPD literature, where we have the friction coefficient equals 4.5, particle density 3, and RC cavity equals 1. And in this particular set of parameters, the Schumpeter number is actually around 0.6, which is more like a gas rather than a fluids. But DPD is supposed to be simulated to behave like a fluid. And therefore, we are thinking about how can we actually increase this Schumpeter number so that it will behave more like a fluids. By looking at this formula here, like cavity is constant, pi is constant, rho d is constant. The only two parameters we can vary is the friction coefficient gamma and also the cutoff radius RC here. But if you increase cutoff radius, it will increase the computational cost dramatically, because it will, like for example, for one particular particle, it will have, if you have a large cutoff radius, it will be interacting with small particles. That will increase the computational cost. Therefore, we decided to go for the friction coefficient gamma, but keep the cutoff radius RC the same. And for example, if we keep everything else the same, but only increase the gamma from 4.5 to 450, we actually have a Schumpeter number of around 1000, which is more like a fluid. So this idea of increasing the Schumpeter number is not new. It was actually mentioned in the famous paper by Groot and Warren, who used to be at the Unilever. And they mentioned that we can have a large Schumpeter number if we use large value of the gamma here. However, if we use large gamma, then if they want to control the temperature of the system, then the step size they use have to be much reduced, which is not ideal. Because if you use a smaller step size, which means that you will have to run the simulation for much longer. if you want to have the same total number of simulation times here. This is probably true at the time, because at the time, the most popular method is like a velocity relay type of methods, where we basically integrate the whole momentum part all together. Therefore, if we have a very large friction, then the distributive term will dominate the conservative term, but also the random term, which is not ideal. But now we can actually do much better than the velocity relay methods in DPD. And particularly, we can use the so-called splitting methods, where we can actually, split the vector field of the whole system into pieces like A, B, and O here. And the A and B together is essentially the Hamiltonian part, and the O part is the distributive term and also the random term here. So this is basically the simple step here. This is basically the Ornstein-Uhlenbeck process here. I'm not going into too much technical detail here, just to mention for the subsystem A, B, and O, we can solve each subsystem analytically. Then we just need to kind of combine them in a certain way, so that we can have a better approximation of the whole system. And this was mentioned in the famous book by Mike Allen and Dominic Kildessley. They have the second version of the famous book in a few years ago, and they have some discussion about the splitting method, but also they have added some more discussion about the mesoscale method. And if you want to look at more mathematical details or discussions, you can look at this book by Ben Lemkler and Charlie Matthews a few years ago as well, where they talk talk about the splitting method in much more mathematical, rigorous ways. And then, as I mentioned, once we do the splitting, we need to kind of combine them in certain order so that we will have like approximation of the whole system. And actually, one of the most popular methods in the DP literature is by Tony Shadrow, who used to be in Manchester, but now he is in Bath. And so what his famous method does is to estimate the O part by one step, and then followed by a half step for the B part, which is and then one step for A, another half step for B. So it's essentially OBAB, OBAB methods. So whenever the letter appears twice, we have to use half step. And we actually came up with a new method, which I term as like ABOBA, because we do half step for A, half step for B, and one step for O, a half step for B, and a half step for A here. And it works really well. And there are two differences between Shadrow's method and my method. One is they use the second order BBK method to approximate the O part. So it's not exact here, but we use the exact solution for the O part for each interacting pairs. So that's the improvement. And also the order, although the splitting is the same, like A, B, and O, but the order is different. Like he uses OBAB, I use like ABOBA here. So just to mention, when we do this like splitting methods, different splittings and different combination will give you very different performance in practice. So you have to be careful how you actually combine them together. And if you are familiar with the splitting method in the Langevin dynamics literature, you might be wondering, why don't we use the optimal OBA methods? Some of you might have seen this before. So the reason is that in the DPD context, the O part also depends on the position or configuration of the system. Therefore, if we use BAOBA in DPD, it will mean that after the A step, we will have to calculate the interaction to compute the O part. But then after the second A part, because after one A part, all the position will be changed. So we have to calculate all the distance again to compute the force in the B here. Therefore, if we use BAOBA in DPD, it will effectively like two force calculations in one step, which will be not ideal. So therefore, we decide to use the above, where we only to calculate the force once in each integration step here. And now we have done some numerical simulations to see how actually they work in practice. And here is we compare the relative error in the configuration temperature, like this one here, that only depends on the configurations against the step size here. So they are both like log-log plot here. And on the left, when the gamma is 200, we can see the velocity, the famous velocity Vallée is somewhere here. But we can clearly see that both splitting methods perform much better than the velocity Vallée here. As you can see, it will become unstable when the step size about 1.01 here. But the other two can use much larger step size. And if we use a much larger friction coefficient here, the velocity Vallée already became already unstable, so we didn't include it in this plot here. But again, we can see in both cases the one I propose is much better than the shadowless method here. For example, if we use a fixed step size, say let's say 0.05, so the relative error is about 1%, but the shadow is about 10%. If we draw a line somewhere here, and let's say if we want to have 10% error, the largest step size that they can use is about 0.05, but then we can use about 0.1, which is like we can at least double the performance. And we also try to quantify the numerical efficiencies. So we look at the largest step size we can use from each of the methods here. And as you can see, in the shadowless method, we can use about just below 0.05. But for my method, we can use just above 0.1. So it's like we can double the step size. And the CPU time is very much similar. So therefore, we can at least, reduce more than 50% of the simulation time comparing to the shadowless method here. And we also compare the shear viscosity. Here we don't use any of the AMD or Norton approach. So here we use the more standard Irving-Cook stress tensor subject to least static boundary conditions. So it's like we share the system. This is more consistent with the real experiments. And then we can extract the shear viscosity by using this formula here. The sigma xy just the xy component of the stress tensor, and the kappa here is the shear rate. And then again, this is the relative error in the shear viscosity against the step size in a log-log plot here. And when the gamma is very large, so it's more like fluid. So again, we can see the above I propose or to perform this like famous the S1 method by Tony Chatelot here. Any questions for this part? I can also carry on if you want. Yeah, I can carry on.
Yeah, 5-10 minutes.
Sure. And for the last part, it's about extension of the so-called adaptive launchman thermostat in the DPD context. So this is basically we did this like a few years ago. The whole idea that in the standard DPD we have like fixed friction coefficient gamma here, but here instead of fixed friction we use a dynamic variable C here. The C is governed by this negative feedback loop. So because you can think this the first term in the C equation as the instantaneous temperature of the system, and this is the target. And therefore, if the instantaneous temperature is too high over this target, it will cool the system down. And if the system temperature is too low, it will heat it up. It works like a thermostat or like air conditioner. And so mu again is a parameter here. And the hope is that if, for example, if we have some additional noise appearing in the system, whether it's coming from the discretization errors or it's coming from some external forces, or as long as they are kind of Gaussian white noise, as long as they are like independent of this noise term here, we will have this like a canonical ensemble distribution like this one. And some of you might notice that the black one is actually the famous Nussel-Hoover thermostat. And as I mentioned, if you have additional term here appearing here, it will only change the distribution of the C here. It will not change the distribution of the Q or P here. And but our goal is to kind of have a a good sampling of the canonical distribution in the, particularly the marginal distribution on Q and P. So it will not change that. This is really nice. And we also claim this pairwise adaptive Langevin or adaptive DPD inherits all the essential properties of the traditional DPD for hydrodynamics, and particularly this adaptive DPD also has Galilean invariance because the damping term will depend on the relative velocity rather than the absolute velocity, and also it has momentum conservation properties, which is very important for the hydrodynamics. And so we look at the dynamical property of the new like adaptive DPD of pad L here by looking at the velocity autocorrelation function. So as I mentioned at the very beginning, if we do an integral of this velocity autocorrelation function, then you can estimate the diffusion coefficient from here. So therefore, it's quite important like stuff to check. And what we can see here is that for wide range of the friction here, the VAF of DPD and the pad L or adaptive DPD, they stay very close to each other, which means that it's, you know, you can view it as like alternative DPD or adaptive DPD here. But the advantage of this new approach is really that, for example, if we again compare the relative error in conversion temperature, the red one clearly outperform the other popular methods in the DPD literature. And particularly here, we also include the Loewy-Anderson thermostat in purple, and also the NOSEF Loewy-Anderson in blue here. So we can clearly see this new method has about 1 order of magnitude improvement in terms of the accuracy here. And also very quickly, finally, I'll mention some application in polymer melts of this new methods. So in the polymer melt simulation, we use this truncated and shift Lennard-Jones or WCA potential together with this Finney potential. And for the Finney potential, in case you're not very familiar, we also have a constraint in terms of the largest bond length you can have, which is Rmax here. If the bond length will be above this Rmax, the bond will break. So this will have some like a restriction on the numerical methods. And so here is how this potential look like. The black one is a Finney potential, and the red one is the original Lennard-Jones potential. So combined together, they will look like the green one here. So here's the results when we compare the sampling accuracies against the relative error in conversion temperature. You can see that for the new methods are proposed in blue here, the accuracy is much better than the original DPD methods in black here. So here we also included some popular methods for Langevin dynamics for polymer melt simulations, and also quickly mention that for the Baoba methods I mentioned, if the friction is very large, you don't have the first order convergence rather than a second order. So it's the so-called the super convergence, and we can also show that why it's first order. And also quickly about this orientational autocorrelation function OAF, which characterizes the relaxation with the polymer in a melt. And what we are finding is that on the left, for a Langevin dynamics approach, actually we will have the OAF will be close to the reference one, even when the gamma is very small. But for the DPD or adaptive DPD, if we change the gamma value here, it will always be like very close to the reference, like OAF will pretend. So this works really nice. And finally, again, the shear viscosity, the same like formula I showed before, but this time we are comparing the shear viscosity against the shear rate. We want to see how much large shear rate you can use for this particular simulation in polymer melts. And what we are seeing here is that for the DPD in green, I mean the traditional DPD in green, it will break when the shear rate is about somewhere 0.00405. But if we use an adaptive DPD, we can use a much larger shear rate. It's almost 1 here, which means you can use a much wider range of shear rate, which will give you much more flexibility if you want to compare experimental results, so which is very nice. And the reason why that's the case is we thought it's because of the negative feedback we included when we came up with the pairwise adaptive arrangement or the adaptive arrangement here. Finally, just some reference. The first one is the original paper about Norton dynamics. The second one is the recent paper by Gabriel Stutz and Noe Blancel, where they extended the Norton to Norton, but mostly the simulation is all about Langevin dynamics. Then we extend this to DPD. The fourth one is where we discuss the Schmidt number issue. The last one is the results on the polymer melts. And with that, I thank you very much for your attention. Thank you.
Junk. Okay.